Great. I've been given 5 minutes to quickly introduce you to Paragraf. I'm going to guess that most of the people in this room haven't heard of us yet. Don't worry, that's soon going to change. But I'll start at the beginning. We're a spin-out company from the University of Cambridge, Professor Sir Colin Humphrey's group, Materials Group at Cambridge, where our current CEO, Simon Thomas, started working on the graphene technology that we use today. The company founded a few years after that, and then COVID happened, and it wasn't great. But graphene electronics, why graphene? Why do we make electronics out of graphene, and why should you care? Basically, graphene is just a really good semiconductor material. It's got great electronic properties, it's got great mechanical properties, resilient to temperature, strain, radiation, you name it, it's probably resilient to it. What do we do with it? Well, we make a few things. Our most mature technology is the sensors side of things. We make Hall sensors. We've also got other R&D activities from biofets, biosensors, and further technologies from transistors to optical modulators to on-chip supercapacitors. You name it, we're probably looking into it. To prove to you that we've actually got something that works, I filmed. You've probably heard of graphene already. I mean, it's been a thing for 20 years. Why has it taken so long to go from the original research in Manchester to a chip that works? It turns out making graphene is difficult, but that's why we're so great. We've figured it out. We've got a process that uses standard semiconductor tools, standard semiconductor processes, MOCVD, for those of you that know about that stuff, and we deposit the graphene directly onto standard semiconductor wafers. What does this mean? It means that we've got high-quality graphene devices that we can actually scale to commercial production volumes. And make things that work better than the silicon devices you're using today, notably silicon Hall sensors. Hall sensors have a wide variety of applications, and I'm not going to bore you too much, but current sensing for battery systems, to MRI mapping in biomedical environments, to cryogenic magnets and fusion reactors and tokamak, for instance. But since this is AESIN, I will focus in on automotive. In fact, you probably know better than I do where to use Hall sensors in the car, so I'm not going to explain it for you. But it can broadly be summarized into two core categories. Current sensing, where we've demonstrated measurements from milliamps to more current than you can put through a wire. And position sensing, where our higher sensitivity just gives you better performance than silicon sensors. If this sounds of interest to anything you do, just come have a chat with me either outside or send me an email or just visit our website. And yeah, always happy to discuss new applications. Thank you very much.